Welcome back to Atomo Tutorials. The last tutorial covered quite a lot on ionic bonding. I'm going to be doing the same, but focusing on a different type of bonding known as covalent bonding. So what exactly is this? Well, a covalent bond is when a pair of electrons are shared between two atoms. This only happens with electrons on the outer shells of these atoms, and it gives each of them an extra electron. If we look at the example of hydrogen chloride, which is actually hydrochloric acid once we put it in water, there is one electron on the outer shell of hydrogen, and there are 7 electrons on the outer shell of chlorine. In order to gain a full outer shell, each atom needs one more electron. So what happens is hydrogen and chlorine both share one electron with the other. Essentially, they both have what the other one needs. So what this does is give both the atoms a full outer shell. In hydrogen's case, 2 electrons on its first shell, and chlorine 8 electrons on its third shell. This bond is very strong, and it lies again behind electrostatic attractions. So the positively charged nucleus at the center of both atoms forms an electrostatic attraction with the shared electrons. This attraction is what keeps these bonds in place, and separating these atoms would mean breaking these bonds altogether. So, in the case of ionic bonding, what happens is electrons are lost and gained by atoms to create ions of opposite charge with full outer shells. These ions then attract each other. For covalent bonding, electrons are shared between atoms to the point where all the atoms have a full outer shell. And the electrostatic attraction which holds the bonds together is between the nuclei, which is plural for nucleus, and in fact I'll write that down just so you know the spelling. The attraction is between the nuclei of the atoms involved in the bonding and the electrons being shared between them, because they are subatomic particles of opposite charge after all. So when we have a couple of atoms, or even a few atoms, covalently bonded to each other, this is known as a simple molecule. They're not like ionic compounds that exist in large lattices. These are individual molecules on their own. Some examples of these simple molecules are things like oxygen and chlorine. And the covalent bonds between the atoms in these simple molecules are roughly the same size as the atoms themselves. Which is very small. Oxygen and group 7 elements such as chlorine exist in pairs naturally. We also have other simple molecules that we're going to look at in more detail, like methane and water. So there are 6 specific examples of these simple molecules that you need to know. And just like with ionic bonding, we're going to look at the dot and cross diagrams of each. And if you understand the concept that I've just laid out surrounding covalent bonding, these shouldn't be too difficult to understand. So we're going to start off with hydrogen. The first thing to know is that hydrogen as a molecule in nature exists as pairs rather than as single atoms. And this pairing is due to covalent bonding. But both hydrogen atoms have one electron on their outer shells. These electrons are shared, and one covalent bond is formed between them to complete both their outer shells of 2 electrons. The next example is the one we've already looked at, hydrogen chloride. It's not too difficult. It's not too different from hydrogen because one covalent bond is being formed between two atoms which only need one more electron for a full outer shell. Oops. I'll just add these electrons in. Now this next one is a bit different, a molecule called methane. Methane is made up of a carbon atom and 4 hydrogen atoms. Carbon has 4 electrons on its outer shell. It needs 4 more electrons to complete a shell of 8. A hydrogen atom needs 1 electron to complete its outer shell, but this hydrogen atom can also supply one by sharing it. As a result, 4 covalent bonds are formed between carbon and hydrogen. Carbon shares one of its 4 electrons with each hydrogen, and each hydrogen shares its 1 electron with carbon. So in this way, all atoms, as you can see, end up with a full outer shell, and we have methane. For water, we have oxygen and 2 hydrogens. The oxygen atom has 6 electrons in its outer shell, and it needs 2 more in order to complete it. The oxygen shares 1 electron with each hydrogen, and this completes the outer shells of hydrogen, but hydrogen of course also shares its electron, and so because there are 2, we can go from 6 electrons in the outer shell of oxygen to 8. Seeing as we're talking about oxygen, the next example looks at the bonding that actually takes place within an oxygen molecule. And much like hydrogen, oxygen is a diatomic molecule, with di meaning 2, because it exists, the atoms exist in pairs. But as we know already, oxygen has 6 outer shell electrons. If each of these molecules share 1 electron with each other, both would have 7. This isn't enough for a full outer shell, and so each oxygen actually shares 2 electrons with the other and forms a double covalent bond between the atoms. So we have 1 bond and 2 bonds. The last example, and probably the most difficult, is carbon dioxide. Carbon dioxide has the formula CO2, has 1 carbon and 2 oxygens. Carbon has 4 outer shell electrons and it needs 4 more to complete its shell. Oxygen, or the oxygen atoms, each have 6 and so need 2 more each to complete their full outer shell. If carbon forms a double bond, which is inevitable because we have oxygen which needs 2 more electrons and we've only got 1 carbon, so that's 1 double bond, and we've got oxygen covalently bonded to carbon. Oxygen has a full outer shell in this situation, but carbon doesn't. Carbon has 1, 2, 3, 4, and these 2, which wouldn't be involved in bonding, 5, 6. That's not enough. So what we do is, or what carbon does, is combine with another oxygen and forms another double bond. And so all atoms here have a full outer shell, and we end up forming 2 double covalent bonds. So looking at various models to represent simple covalent molecules, dot and cross diagrams are again good at showing how covalent bonds form in terms of electrons. They don't show, however, the molecule's 3D arrangement, and diagrams like this, which show the shared electrons but don't show the electron shells, don't take into account the relative sizes of the atoms. Displayed formulas look like this and have lines representing covalent bonds, gives a basic 2D representation of the molecule, and it shows the atoms and the bonds, but it doesn't show which electrons the atoms come from, as obviously as the dot and cross diagrams do. Despite this, you should know that one covalent bond means that one electron from each atom has been shared with the other. So you should be able to look at this, and knowing what you know, which in this molecule is called ammonia, by the way, knowing what you know, you should know that nitrogen has shared 3 electrons, one with each hydrogen, and that the 3 hydrogens have each shared an electron with nitrogen. And again, these diagrams don't show the relative sizes of the atoms. The last structure, or the last 2 structures really, ball and stick models like this one and other 3D models like this one. A good thing about these is obviously the fact that they're 3D, so we can get to see the structure more realistically, but this does have its downside. If you have a large molecule with many atoms, the 3D structure tends to become more complex and could be confusing to look at. Also, like before, it doesn't show where the electrons have come from, but we've already said why. This doesn't really matter too much. And lastly, ball and stick model suggests that there are gaps between these covalently bonded atoms, which just isn't the case. But just like last time, these models are useful for different things. If you want to learn more about the concept of electron sharing and covalent bonding, then dot and cross diagrams would be best. If you're very familiar with it, I would look to the other models depending on the size of the molecule.